Good evening, colleagues, ladies and gentlemen. It gives me very great pleasure to welcome you here to Leeds Beckett University and, more importantly, to the inaugural Professorial lecture of David Johnston, Professor of Building Performance Evaluation. As a university, we have a unique opportunity to contribute to social and economic progress in our region and for our region through our research and enterprise. And in recent years, we've demonstrated significant growth in our research capacity as we continue to expand and enhance our research base through our institutes and our centres and create a strong and sustainable research environment for our staff and for our students. Every year we contribute an estimated £500 million to our local economy, and with strong commercial links, our research is applied directly to industry, providing practical solutions and innovation for businesses and for other organisations. We cover a wide range of research disciplines, and in tonight's lecture, Professor Johnston will draw on his research to examine the building performance gap, the building fabric performance gap. I do apologise, David. David joined our university as a research assistant in 1994 after completing his MSc in Energy Systems and the Environment at the University of Strathclyde, where he was employed to work on a number of field trial projects regarding energy efficient housing. In 1997, David took up a lecturing post at our university within the School of the Built Environment, where he changed career direction and began teaching construction technology, environmental science and building services to a wide range of undergraduate built environment students. Throughout his teaching career, David has continued to be involved in low energy housing research projects, ensuring that his research findings informed his teaching. After lecturing in construction for almost 10 years, David was promoted to readership at our university in 2007. Enabling him to develop his research interests in low-energy housing, principally in the areas of building airtightness, co-heating testing, and building performance and evaluation. In a career spanning more than 20 years, you wouldn't think it to look
You've aged a bit.
David has worked with a wide range of organisations, including registered social landlords, government departments, other academic institutions, and major house builders. He's developed a reputation as one of the leading experts in the UK on both co-heating testing and building performance evaluation. Ladies and gentlemen, it is my very great pleasure now to invite the main actor of the evening, David Johnston, to present his inaugural professorial lecture, Bridging the Building Fabric Performance Gap.
Thank you. Tonight, I'm going to have a look at bridging the building fabric performance gap. So in terms of the structure for this evening's talk, first of all, just look at the context in terms of it's all set within a domestic context, looking at dwellings in the UK. Some of you here, colleagues of mine, you know what the performance gap is, but for the rest of you, we'll define what we mean by the building fabric performance gap, and then the fabric performance gap. We'll look at techniques that can be used to quantify the size of a performance gap. We'll investigate whether it's actually possible to bridge a performance gap, so the title of tonight's talk. Some other work which looks at a meta-analysis of some data we've got at Leeds Beckett University, where we're looking at quantifying the scale of a performance gap. And finally, just concluding at the end, and then I'll take some questions. So in terms of the context, in terms of UK, the domestic sector, like most industrialised countries, contributes substantially to energy use and CO2 emissions. In the UK, about a quarter of all end-use CO2 emissions are attributable to dwellings, and about 30% of energy use is attributable to dwellings. We all live in dwellings. There are more than 27 million in the UK, so it's a substantial component of the built environment. And they are quite unique in the sense that they have very long physical lifetimes. So there's a lot of dwellings around which have been around for a very long time, unlike non-domestic buildings which have much shorter lifetimes, generally speaking. And stock turnover is also very slow. We haven't gone through any mass demolition programs, certainly for about 50 years or so. And unless we do that, the chances are that we're still going to be demolishing very few dwellings as we move forward. If we're going to meet national CO2 emission reduction targets, so an 80% reduction in national CO2 emissions by 2050, we're going to have to do something to the domestic stock, to existing dwellings and to new dwellings, because they'll make a significant contribution to any CO2 emission reduction targets that we achieve. And there's also, the government's got a commitment that all new dwellings are to be zero carbon by 2016. So that sets the context for tonight's talk. In terms of what do we mean by the performance gap, well, traditionally, in terms of performance, we're looking now at new dwellings, it's traditionally taken for granted. Developer comes along, builds a new dwelling, and it should perform a lot better than existing properties, certainly older properties, or that's a theory anyway. There is mountain field evidence that dwellings are not performing in situ, certainly within the last 4 or 5 years. Predominantly there's been a lot of, the industry will say there's not a lot of evidence, but there's quite a bit of evidence coming out that they are not performing as they should do, as they were originally designed to do, and that means in terms of the design intent. Even if we take into account, generally speaking, even with domestic buildings, developers don't tend to build what they originally set out to build. Changes happen on site. We have to make up details because we don't know all the drawings are available. Product substitutions occur. So what's actually built in practice tends to be quite a bit different from what was originally designed. Not enormously different in terms of the actual form and aesthetics of the dwelling are probably pretty much the same, but they may be constructed from different materials, and some of the details might not be quite as they were designed as well. So even if we take into account all the changes which are made during the construction process from how it's designed, when we actually come along and predict the performance based on as best informed information that we have about what's physically been constructed, there is a gap between what the predicted performance is and the measured performance. So that's us little green man there scratching their head, wondering, well, how's this happened? And in some cases, the difference between predicted and measured performance can be quite large as well. And that's what we refer to as the performance gap. So this gap between predicted and measured performance. And it's obviously quite important if you design a building and construct a building to achieve a certain energy consumption or a certain fabric performance, and it achieves something quite different. That can have quite significant consequences for the occupants of that particular dwelling. In terms of the factors that contribute towards the performance gap, well, there are 4 main factors. 3 which we have control of, and 1 which unfortunately we don't have control of. We just have to live with. There's fabric performance, which we're going to look at tonight. So that's the elements of the building, the floors, the walls, what we're constructed of. That can have an impact on the performance of the actual dwelling itself. And we're beginning to get a reasonable understanding of fabric performance. It's certainly considerably more information than we previously have had. There's also services performance as well. So the actual services that go in, the heating system, the ventilation system, any lights that go in there, they can have an impact on how the building performs. So even if it's very well insulated and airtight, the services quite often don't perform quite as well as they should do. And in the most severe instances, they don't perform at all. And then there's us, the occupants, who, it doesn't matter how well you design the building, how well insulated, airtight, you could have some fantastic services in there. If us occupants come along and don't know how to use that equipment, or you know how to use the building, we can have a significant impact on the energy use and CO2 emissions as well. And then there's the external environment, which we don't have any control over. Or we can design to try and control it to some degree, but generally speaking, there's a limited amount of control over that. And it has an impact on fabric services and occupants as well. In terms of building fabric, thermal performance, well, thermal performance of dwellings is incredibly important. It can have a significant impact on energy use and CO2 emissions. If we are to move towards zero carbon house in 2016, we have to have very airtight and very well insulated houses. That's a given. In terms of fabric performance, we've pretty much just assumed that we design the building, it complies with building regs. The amount of insulation that we've designed goes into that building, that goes in the correct way, and the building performs pretty much as it should do. So performance is taken as being granted in terms of fabric performance, but in reality it's actually really understood, and we've got very limited knowledge about the actual true fabric performance of the entire dwelling stock, either existing dwellings or even new dwellings. Construction's a rather strange industry because it's one of the few industries which doesn't actually test any of its products once they're built. You couldn't get away with it with other industries like cars. But in terms of mass just commercial house building, we don't do any testing work. Certainly not in terms of fabric anyway. For some testing that goes on in individual components like boilers in the laboratory, but not in situ. So it's therefore essential that we find ways to bridge this performance gap, so close the gap between predicted and measured performance so they actually perform as they should be predicted to, and then hopefully much closer to how they were designed in the first place as well, to the original design intent. There are a range of techniques available in which we can measure building fabric performance. We've got thermal imaging cameras, so we can look at particular elements of a building fabric and determine whether there's insulation, whether there's air movement through the fabric. We can drill holes in the fabric, we can take temperature measurements, we can do airflow measurements as well to work out if there's air moving through. We can do some partial deconstruction, which is not always the case, but take parts of a building apart to see if what should be there is actually there. Developers don't like us doing that sort of thing, for obvious reasons why, because we usually find things which we'd rather we knew nothing about. We can do heat flux measurements. This is where we put heat flux plates on the wall and we can measure in situ U values, and we can do pressurization tests as well, and pressurization tests are incorporated within the building regulations. So that's the only type of test which has to take place in terms of new building and within a certain proportion of new dwellings and non-domestic buildings as well. So in terms of is it possible to bridge a performance gap, as part of this talk, I'm going to have a look at two recently constructed passive house projects which were tested as part of TSB, Technology Strategy Board Building Performance Evaluation Project, and now called Innovate UK. This is an £8 million programme funded over 4 years, and the aim of the programme was to begin to understand the factors that influence the performance of buildings and gain some more evidence in terms of predicted versus measured performance. The funding was evenly split between domestic and non-domestic buildings, so 4 million each, and the two projects that I'm going to look at in detail to start with are phase 1 projects. So they were designed to look at the building pre-occupation, so purely as it was constructed and before the occupants actually moved in. And that required a number of tests to be undertaken. In terms of the two case studies to look at here, it's 3 dwellings in total, 2 from one site and 1 from another site, so two sites in terms of case studies. One of them is a Gen 2 racecourse development at Hottenley Spring in Sunderland, and the other one's a Lancaster co-housing development over in Lancaster. The Gen 2 development, there were quite smallish developments, but I suppose reasonable size given the sort of economic downturn. 28 bungalows designed for elderly residents. They were arranged, the majority of them in row terraces. 25 of them there were 3 detached bungalows. They were all designed to the same standards, but 25 of them were designed to achieve passive house certification, and at the time it was the largest passive house development in the country. In terms of the Lancaster development, they were all designed to passive house standards, and it was the second largest development in the passive house development in the country, but the first to actually try and achieve passive house certification and code for sustainable homes level 6. In terms of the actual dwellings itself, we're going to look at the results from them. In terms of the Gen 2 passive house development, it's these 2 properties here, which we'll be referring to as dwelling 1A and 1B. And in terms of Lancaster, it's this end terrace here, dwelling 2. They're both roughly the same sort of size, about 65, 66 metres squared. The Gen 2 ones are actually, of all the bungalows, we have, they're sort of 1.5 storey, we have a mezzanine plant room. They are timber frame construction, and then the contrast with the Lancaster ones, which are full fill masonry cavity construction, so a much more traditional construction of a much greater amount of insulation within the walls. Cold pitch roof construction in terms of Lancaster, and warm pitch roof construction in terms of Gen 2. In terms of the tests that were performed, a range of tests were required to be undertaken as part of a Technology Strategy Board programme, and they were supplemented by significant amount of qualitative information as well. So we observed the dwellings as they were being built, did design reviews, did some sort of very early occupancy analysis as well. But in terms of the actual fabric testing, principally we undertook pressurisation tests with leakage detection, heat flux measurements. So pressure tests with leakage detection was to determine how airtight the dwellings were and where the leakage paths were. Heat flux measurements to determine in situ U values, so to be able to compare the U values that were measured in situ with those that they were designed to achieve. And then the coheating test, which we've developed, and myself and colleagues at Leeds Beckett University, and some who are no longer at Leeds Beckett University, developed a protocol to undertake a whole house test to determine the heat loss from an entire house based on work that was done in the United States in the late 70s, early 80s, 1980s. And the heat flux measurements were undertaken during the coheating test, because the coheating test itself provides ideal conditions to undertake heat flux measurements. What the coheating test does is we heat the dwelling artificially to an elevated mean internal temperature using electrical resistance heaters. We use fans to move the air about, so we heat it to typically 25 degrees centigrade, is the temperature we use in the UK. We measure all the electrical energy going in to the fans and the heaters, and we measure external temperature conditions as well, and we can then plot the power that's used for all the fans and heaters against the temperature difference when we can then correct the data for solar radiation and potentially wind, and we can end up with a heat loss coefficient for the actual dwelling itself. So determine an instantaneous heat loss for it. In terms of the site observations, as we expected with a passive house development, so they're designed to be very well insulated and very airtight. Construction on both sites, on all three dwellings, was to an exceptionally high standard. So all the insulation was in the walls, there was no gaps in the insulation. They paid particular attention to the intermediate floor junction. In this case here, it was parged prior to them installing the intermediate floor, to make sure that it formed part of the air barrier. So there wasn't any air leakage there. Use of appropriate tapes, they were wet plastered. And on the Gen 2 ones, again, using appropriate tapes where there was any surface penetrations through the building as well, and paying particular attention to the air barrier and the vapour barrier as well. So there's considerable effort put into these dwellings to ensure that they would meet passive house standards. In terms of pressurisation tests, the results of the pressurisation tests. As part of the coheating test, we do a pressurisation test prior to undertaking the coheating test, and then one at the end, and take the average of the two when we're working out the heat loss coefficient for the dwelling. The top pictures relate to the Lancaster coheating dwelling, and the bottom ones to Gen 2. And as we expected, there were very, very few leakage points. They were very airtight dwellings. In terms of Lancaster, there was some underneath the kitchen sink and around the patio doors, sort of common areas that we normally see air leakage. And Gen 2, there was the space heating system comprised a communal boiler which served all 7 dwellings in the terrace. So there was a communal heat main running through each dwelling, so there was some leakage around there. And they'd actually been knocking some holes in the plasterboard as well. There was a service void behind the plasterboard to actually get some various cables in for an alarm system. And there was a bit of leakage round the door as well, but not an enormous amount, not what we'd normally see in normal mainstream housing. However, both the Gen 2 dwellings and the Lancaster dwellings were leakier than were originally predicted. So they were leakier than they perhaps should have been. In terms of Gen 2, it was because of leakage around the communal heat main and the holes in the plasterboard. And in terms of Lancaster, it was really around patio door and service penetrations under the kitchen sink. So that gives us some idea as to where perhaps, if there is a gap in performance, where some of that may have occurred. In terms of measuring U values, so measuring the in situ U value of all the plane elements, the walls, the floor, the ceiling. A whole range of heat flux plates were installed in the dwellings, up to 20 in each dwelling on the main thermal elements. And the majority of the elements actually performed pretty close to the specified design U values. The only real discrepancies were in terms of the Gen 2 dwellings, 1A and 1B. There was some discrepancy with roof detail, and that was mainly related to the position of the heat flux plate, because it was very close to the eaves junction, rather than to the actual performance of the roof itself. And the external wall in Lancaster was a bit higher than design, and that was mainly due to a thermal anomaly, which unfortunately we hadn't picked up prior to its placement, but externally there was an anomaly directly correlated on the outside of that wall, this slight patch here, which could give rise to some of the difference. And also one of the problems with very small dwellings is it's very difficult to find large expanses of wall, where you north facing wall, where you can actually put the sensors on to obtain relatively accurate in situ U values. We also undertook thermographic surveys as well. Again, they identified very few thermal anomalies at Gen 2. It was really because there was some detailing which hadn't been finished around the windows on one of our properties. And in the ones at Lancaster, there was thermal anomaly in the external wall. They had some issues getting the insulation in the loft right into the eaves to a sufficient depth. So they'd had to cut a hole in there was no loft hatch, they had to cut a hole into the ceiling, gain access. And as part of that process, it's very difficult once you cut a hole in the ceiling to get the insulation to come back down onto that ceiling once you've done it. So that was part of the issue as well. And there were some issues round about the actual edges of the lintels on the windows as well, which may have been some sort of residual construction moisture or a discontinuity in the insulation around the cavity tray. Very difficult to know exactly what they are unless you do actually partial deconstruction. And with them being passive house developments and occupants desperate to get into them, it just wasn't possible, unfortunately, to do that using sort of non-destructive testing methods alone. In terms of coheating tests, and this is really the key one, in all three dwellings, the measured heat loss coefficient, which was the output from a coheating test, was greater than the predicted heat loss coefficient. But in each case, the difference was incredibly small. So the actual gap in performance between measured and predicted was very small, and it's certainly the smallest gap that we've ever measured before in all our experience of undertaking coheating tests. In order to be able to just put some context to those figures, we compared them to a database of coheating data. And this database represents almost a decade's worth of work at Leeds Beckett University with myself and colleagues. It's the largest database of its kind in the UK. It has information on new build dwellings, existing dwellings, range of different construction types, ranging from timber frame, one hemcrete dwelling, to masonry cavity construction. Some are passive house dwellings, some of them are not, some of them are more mainstream housing. Includes apartments, semi-detached, various different forms as well. New build and existing, but in terms of new build, which we're specifically looking at tonight, it's just 25 dwellings. We've done over 50 tests, probably closer towards 100 tests, and some dwellings have been tested multiple times. So they've been tested and interventions taking place, so the cavity walls being filled, for instance, with insulation, and then the dwellings been retested. And in terms of the new build ones, they were all tested very close after practical completion, prior to the occupants moving in. Apart from one at Lancaster, the occupant was decanted and then moved back into the property, but she'd been in the property only a short period of time. And they were all built to Part L1A of the Building Regs 2006 or better. However, most of the dwellings, in terms of the new build dwellings, it's a non-random sample. Unfortunately, we've only been able to test the dwellings which become available, which form part of projects like TSB BPE program. They tend to be low energy developments. So you would think that this is, in terms of context, probably giving you a slightly skewed picture, probably giving you a better picture than perhaps may be the case with normal mainstream housing. If we actually look at the database and just ranked them in terms of highest predicted heat loss coefficient to lowest, it's quite clear the case study dwellings stand out a mile. As you would expect, the passive house developments compared to the rest of the developments, very low heat, but very low, very well insulated and airtight, very low predicted heat loss coefficient to start with, and the actual measured heat loss coefficient was very, very close to that, incredibly close. But you can see the range of performance that we have within that database, so quite a wide range. And bearing in mind, as I say, that these are low energy dwellings, this is painting possibly a slightly rosier picture than might actually truly be the case if we're looking at more conventional mainstream housing. So what this sort of indicates is that all three case studies perform very close to that. The measured performance was very close to that was predicted. They're in quite stark contrast with the majority of data that's available on new build housing. And what we do suggest is the size of the gap is small enough that it is technically possible, practically possible to bridge a gap between measured and predicted fabric performance in new dwellings. The questions are, why did these dwellings perform quite as well as they did in comparison to all the other ones? The sort of golden question, and what the answer everybody wants to know. Well, in terms of these dwellings, they were passive house dwellings, so they had very stringent design requirements to start with. As part of a passive house certification process with a whole range of additional quality control procedures which were put in place as these dwellings were being constructed. They were tested, air tested partway, pressurisation tested partway through construction, and that's not the norm for mainstream housing. So that could perhaps be part of the reason why. They're also designed and built by a highly skilled, educated and committed team. So they had experienced passive house designers and who were doing the design. The designer was on site constantly feeding back to the construction team, and in terms of the construction team as well, they all had a vested interest in the dwellings and the performance of the dwellings ultimately at the end. And they were also high profile developments because they were the first of a kind. Obviously the price of failure was considerably higher than if it's just conventional mainstream housing as well. So these are probably the reasons why these dwellings performed quite as well as they actually did. If we actually go back and have a look at the coheating database, there's some other information that we can get from this which is interesting as well. If we try to do a meta-analysis now, as I say, you just have to bear in mind that it's a small non-random sample, 25 dwellings in total. If we actually plot measured consumption against predicted consumption, this is the sort of performance gap. Again, this is what we would expect if measured and predicted were the same, which ideally that's your ultimate goal effectively. You can't have measured consumption lower than prediction, otherwise either your prediction's wrong or the only way you can do it is by putting more fluff in than should be there, but that means that your prediction should be tweaked accordingly. So this is the sort of scale of this, generally the scale of a gap. If you do some very simple linear regression analysis, it's about one based on the sample we've got, it's about 1.4, almost 1.5 times the steady state prediction. So that's got significant implications in terms of design, construction, and trying to achieve any CO2 emission targets if the data we've got suggesting that the heat loss coefficient is going to be almost 1.5 times what it should be from the actual outset. And that's bearing in mind the actual sample we've got, best case. It could be considerably worse than that. If we actually just look at the size of the discrepancy in percentage terms between measured and predicted performance, it's actually quite alarming. We've got it ranging from very small, 6% for the passive house dwellings, and that's because if you have a disproportionately high percentage discrepancy because they've got such a low heat loss coefficient to start with, up to 140%. So it's quite alarming when you actually look at it at that sort of scale. Although you do have to just treat discrepancy with caution because it doesn't take into account any factors such as the dwelling form, the size of a dwelling at all. So you just have to be careful with that metric. A more appropriate metrics to look at whole building U value. So if you take the ventilation heat loss out and then just look purely at fabric heat loss, whole building U value is a better determinant at looking at the performance of the actual dwellings. And you can see here that there's still a very wide range of performance. Measured U values ranging from 0.18 to 1.05. Whole building U values were predicted from 0.17 to 0.52. And if you actually look at it in terms of a probability distribution, for a frequency distribution, you can see the range of predicted U values is quite narrow, but in terms of the actual measured performance, it's very, very large. Quite a distinct difference between the two. If you actually look at the data as well in terms of whole building U value, the performance gap is about 1.7 times. So it gets slightly worse if we strip ventilation out of the equation compared to just looking at measured versus predicted to start with. You've got a number of significant outliers there as well. And then if you look at the data in terms of dwelling form to see if there's any messages, I mean, again, you just have to remember it's a very small database, but it is the largest single database that we have of its kind. And all the tests have been undertaken by not necessarily the same team, by the same organisation using the same protocols, so there's consistency there. There's some messages that start to begin to come out. Detached dwellings tend to perform much better than other dwelling forms. With mid-terrace dwellings, there's only small numbers tending to be, generally speaking, the poorest performing. Part of the reason for that's most probably because all the mid-terrace dwellings had a cavity party wall, and they were tested. They were all being built to comply with 2006 building regulations. So at that time, the U values associated with party walls and the party wall bypass had not been addressed by the building regulations. So the predictions for these dwellings don't take that into account. Then if we actually look at construction type as well, there also seems to be some messages coming out in terms of construction type. The best performing construction type tends to be timber frame and structurally insulated panel systems, and the poorest performing, and it's no real surprise for us involved in doing testing, is partial fill cavity masonry. Part of the reasons why that's likely to be the case is with partial fill cavity masonry, it's very difficult in terms of there's a range of issues associated with assembly, trying to make sure that the partial fill boards are flush against the block work in a leaf. Otherwise, there's a risk of thermal bypassing occurring behind the insulation. Also making sure that all the junctions between the insulation are taped. And partial fill is also highly susceptible to wind washing effects as well. So it's not necessarily quite as robust a construction of others. But again, these are just very, very preliminary findings based on what the database that we have. And there's obviously considerable work needs to be done to increase the amount of data within that database and see if these sort of inferences actually change. So to conclude, there is a significant building fabric performance gap in new housing. Looking at the data in terms of whole dwelling U value, which is probably one of the most appropriate metrics to use, whole building U value is, based on the data we've got, about 1.7 times greater than that predicted. There appear to be differences in terms of dwelling form and construction type, which can have an influence on the size of a performance gap. Although we just have to be a little bit careful with form because it may just be due to some of the data that we've got. The most important message, because a lot of the work we do is actually tends to find fault with what's wrong with buildings, that's just the nature of the work that we do. It's always nice to come out with something that's actually positive, is that we can actually, irrespective of how poor we may think some of new build housing actually is, we can actually construct new dwellings that do perform pretty much as predicted. So pretty much bridge the performance gap. Although it takes it's not going to be easy to achieve that within mainstream housing. We need a much more highly skilled and educated workforce which is aware of the issues which can contribute to a degradation in performance. As they're constructing the actual dwellings themselves, we're likely to require the implementation of a whole range of quality control procedures which are not in place at the moment in mainstream housing, more akin to what's in place in terms of passive housing design and those that achieve passive house certification. So the key challenge is going to be how to replicate this in mainstream housing. Can we make sure that the workforce is more educated, more highly skilled, more committed to building dwellings that actually perform? Can we implement quality control systems to make sure that it's one of the few industries where if you go to a lot of the major house builders, we don't really know, bizarrely, what their houses actually are built of. Whereas if you go to a car manufacturer, they'll be able to tell you every nut and bolt exactly where it's gone into a house, into the car. Whereas in terms of house building, quite often what they think it's built of is not exactly what it's built of at all, but they don't know what changes have been made. The construction manager may know, but those sitting in the boardroom don't generally tend to know. And it's likely to require a cultural shift within the industry towards much more performance-based construction. So in terms of construction, we don't test the performance of the product, the house at the end. And it's very unusual within most industries not to do that. So we do some testing in terms of pressurization testing, but we certainly don't do. I'm not suggesting here that we have to test every house, but at least there has to be some testing process in there to make sure that we're actually confident that what we're constructing is actually going to perform and doesn't either have a detrimental impact to the environment or to the occupants within the building as well. So that's all. Some acknowledgements there. A couple of colleagues have provided some graphics. Dr. Jez Winfield he was the original founder of the Coheaton database, and also for the funding provided as part of the TSB Building Performance Evaluation Programme as well. So, thanks very much.
Well, thank you for that. A most interesting review of some of the work I knew was going on. Chris has been telling me for ages about this, and Malcolm too. Very interesting to hear about it. We're now open for some questions, but I'm going to take sort of ringmaster's privilege here and ask the first one. As I understand it, there aren't many new builds happening compared to the stock we have. Is there anything in your whole career to date, including this, that could help people like me who own a house built out of random stone and stuff? What lessons have you learned throughout this research which could help the existing stock holders, shall we say?
Well, colleagues have certainly been involved in doing quite a bit of work on retrofitted properties as well, and we can perform Coheaton tests on retrofitted properties, existing properties as well, although it does require the occupants to be decanted because the test requires there not to be any occupants within the building while it's taking place. So some of the work that we have been involved with is looking at intervention measures, so looking at retrofit stages, so cavity wall insulation, external wall insulation, internal wall insulation, and looking at how it performs in situ, looking at how it's been installed and looking at how it performs in situ, and seeing whether the actual savings that are claimed from the products actually occur in practice when the occupants go back in as well. And we're working with some industry colleagues in here today who were involved in projects which are specifically addressing existing stock.
Okay, thank you very much. Right. Well,
I'm going to exercise a perk as well and ask a question. At the end, when you were talking about the cultural change that was needed, what was going through my mind was how we compare with other European countries, and particularly Northern European countries, which may have, in many cases, smaller house building industries, but possibly a more highly skilled and educated workforce. And if you have any thoughts on that?
They may have a more highly skilled and educated workforce, but they still do not performance test. We are one of the few countries that's we've done more performance testing probably than anyone else in almost, well, certainly within Europe anyway. So even the Germans who developed the passive house standards, they don't have done very few coheating tests to work out the real performance in situ. And also they don't regularly do in situ heat flux measurements either to work out in situ U values.
So, on the back.
No, I agree with you about sort of trying to get a more trained workforce, etc. But one of these sort of options to move more towards off-site manufacturing as a methodology.
So yeah, I mean that's one alternative, but there's some examples that certainly colleagues have worked on where that can go disastrously wrong, where panels arrive on site and they're installed upside down. The insulation's been saturated and not stored correctly, and they had to rip the face off the panels and take all the insulation out. It may be part of the answer as long as the actual it's followed the whole way through and the whole process is robust. But it's not. There's no guarantee unless you actually
predictability of like the performance of a construction material under those controlled conditions. That's something that you would need to be putting forward to actually sort of.
Yeah, you can put much greater control on what actually arrives on site, so you actually know exactly what's there. How it performs in situ will, I mean, to a large degree, you're going to be dependent upon external environmental conditions as well. But at least you can control exactly what's on site. Hopefully, if it's a robust solution, how it's actually constructed on site as well. So you're actually minimising some of the potential errors, or potential discrepancies, which can contribute, or differences, which can contribute to discrepancies in performance on site.
I'm a CIBC engineer. Just two quick questions. Can you remember what the results were on the air permeability? And also, the 1.7 on the U value, that's across that whole.
That's a whole building U value, It's it's over the whole, but over for 25 dwellings,
Right, and it's like the kind of benchmark would be what is supposed to be in building regs at the time, and then compared to what you tested with the coheating.
It would be, the benchmark is what we would have predicted based upon site observation. So what our knowledge of exactly what was built, rather than design intent, which is quite often what happens within construction is they design to meet the regulatory requirements, and then what happens on site is product substitutions and various things change, and what you actually have is a building which may be slightly larger, maybe slightly smaller than you originally had, and has got different construction details that may have a completely different roof construction, for instance, than what was originally designed in the first place.
And the
In terms of air permeability, those particular dwellings we didn't do any passive house air leakage tests, and the methodology is a little bit different. They were, I think the air leakage rate was about 0.8 for two of the dwellings and about 1.3 for the others. So they were quite. They were very good, but they were quite a bit away from 0.6 air changing there for passive house standards.
I've got a queue building up here, at the back first, and then there, then there. Yeah.
It's partly an observation as much as a question, Dave. I just noticed that Gen 2, the actual U value for the wall was 0.18, achieved 0.18, for the roof 0.13, and the observation is that that is just about what's required under Part L1A 2014 to comply with that.
Yeah, 0.18 was Lancaster. Lancaster. Yeah.
So building to kind of passive house standard, in practice just kind of meets current building regulations?
I mean, they're significantly below current building regs in terms of the heat loss coefficient. The heat loss coefficient is about 45 watt Kelvin as opposed to somewhere more towards about 100, 150 for, or certainly probably about 150 for standard building regs house. The problem with the U value at Lancaster was, in terms of heat flux measurements on, you need to undertake them on a north facing wall, and unfortunately because the dwellings were so small, on the ground floor that's where the kitchen and toilet was, and on the upstairs that's where a lot of the glazing was, so we were very limited as to where we could put the heat flux sensors, and most of the heat flux sensors were influenced by some form of junction, so we're very close to junctions, closer than you would ideally like them to be, coupled with the fact that there was also a thermal anomaly on the external of the wall as well, which we never really got to the bottom of what that was. So that U value is I mean, it was as representative as we could get, but we know it's still high compared to the rest of the envelope.
And then the question bit was, do we have any idea of what it costs to achieve these higher levels of efficiency? Because I think that's where stuff has been derailed so far.
Yeah.
If you look at Briand, for example, then the difference in cost between, say, achieving excellent or outstanding, there's a step change. It increases very, very rapidly. I'm just wondering at this level of sophistication.
Yeah. In terms of Gen 2 is a difficult one, a very tricky one. It's a very unusual project. I think it took almost 4.5-5 years from initial breaking ground to the dwellings being completed. Timber frame manufacturer went out of business. They were on the third timber frame manufacturer when they completed, who then, because of a recession, went out of business. So, and they had significant on-site. They had to delay construction on site for about 8 to 9 months because of services which weren't identified within the original site investigation. So Gen 2, the costs are very difficult to get to the bottom of with Gen 2. Lancaster, on the other hand, was a co-housing scheme, so a very tight constraints, so they were funded pretty much by themselves. So they're probably not too atypical from mass produced housing, a bit more expensive but not too atypical. So it's quite a good example of the Lancaster one. Although it didn't perform quite well, unfortunately.
We'll take Yayan and Fazed, and I'll try to answer both while I deal. Okay?
Well, the questions that I've had on U values have already been taken, so I'll pick up a more lay question. I suppose as a consumer, what I'm interested in is, it comes to the last statement about how do you change the culture. It strikes me that with such a disparity between what I'm buying for my money in terms of wanting an efficient house to what I'm actually going to get, I'm surprised almost that there isn't more routine testing of this as part of the regulation. Yeah. And so the kind of that changing the culture is, where does regulation and more use of this testing play a part? And then where that isn't delivered, how do I get a refund, or how does that impact me? If I buy a car because I think it's good to be if I'm buying it for 50 and what I get is 100, I'm not getting, and if I bought off plan. So where does that factor into the regulation? Really?
Now, Fazed, if you pose your question as well, and then ask David to answer that.
Can I start with a comment first?
You may.
Thanks. In fact, I shared that comment with Dave regarding about for the benefit of others. I sit on the Accredited Council, the European Construction Council for Research, Development, Innovation, etc., which is, we get to hear about this big news about construction funding about 3 months before everybody else. And I gave the good news to Dave and possibly to Malcolm and Chris that one of the 5 areas of big investment by Europe in construction is going to be precisely the same title as is up there in the gap. So we are pretty much ready for
Europeans have hijacked our title, David.
No, this is one of the big areas. So, but my question actually is about there are 5 case studies in BRE at Watford where we got high level BREEAM performance of 6, etc. one of the problems they identified is that when we got properties with no leakages, then we got other problems. We have to put in installations in order to recirculate the air, etc. So where is the trade-off there? Are there any challenges?
Okay, so we've got a question on the cultural
Yeah, no, just-
side, and then there's
Yeah.
Fazer's more
I
technical.
remember Fazas first, so.
Yeah.
So, it's the old adage, you build tight, ventilate right. As long as you can build the dwelling as tight as possible, as long as you have an appropriate ventilation strategy in place. And for passive house developments, that's a mechanical ventilation heat recovery system. Unfortunately, passive house is slightly different. The developments we looked at performance of the mechanical ventilation heat recovery units, and they did do what they said basically on the tin. If you think fabric's bad, services is a complete nightmare. It's much, much worse. The advantage with fabric is you can make a dog's breakfast of it, and you'll still get some shelter, and you can still retain some of the heat that you produce within the building. With services, unfortunately, if you get it wrong, it just won't work. So it won't provide any service whatsoever. And we've seen some cases where that happens. And to some degree, it links on to your question, Ian, is how many occupants actually know whether a building's perform? If you're happy paying what you pay to heat the property, to ventilate the property, unless fuel prices rise significantly, you then maybe begin to question that. But how are you to know whether your boiler's performing correctly? How are you to know whether your walls are performing as well as they should do? Unless you've got, drafty areas, cold spots, the chances are that it isn't performing as well as it should do. The evidence suggests it certainly isn't. The question is, where is it on the scale of the performance that we've looked at? But you don't know because nobody tests it. And you just don't have the knowledge to know whether it's right or wrong. So there is a case for certainly regulation, and certainly in terms of regulation, there has been the introduction of pressurisation testing, which has brought about improvements in terms of airtightness. And we're not suggesting here, I'm not trying to suggest here that every house should be cold heating tested. Well, that would be possibly ideal as far as we are concerned in terms of a research outfit, in terms of income. Probably drive us nuts actually trying to do it. But certainly in terms of how industry is looking at it, and certainly in terms of prototyping, certainly looking at it, it's more about introducing more robust construction techniques and the quality assurance processes to know what are you actually building, and are you building it the way you should be building it, and are there other tests that will be maybe simpler, cheaper tests that we can undertake to at least guarantee some degree or proximity to the performance that you should do.
Okay, great. And now, I have 4 people queuing up. Okay, these will be the last 4 questions. I'll ask the questioners to put their questions succinctly, please, and David to address them relatively succinctly.
Right,
Otherwise,
I'm not sure if I can do it.
whatever you have planned for after this event will be delayed. Okay, so you, sir, first.
Yeah, you're starting with a very ambitious sounding government target for 2016. And after that talk, it seems even more ambitious. So my question really is, to what extent do you think that target is likely to be met? And secondly, how will we know?
Unless we test, we won't know, and it's going to be trade-offs with carbon offset and various different technologies which will offset some of the performance gap anyway. So that's how they do it. It's been the watered down in terms of offsetting, so we won't be truly zero carbon houses.
I work in building control, so I've seen a few houses. The house builders are not interested in this, and the system is not interested in this at all. You've got house builders in Leeds. We've got a site starting in the last couple of weeks, and they're building to the 2006 regulations.
Yeah.
So and before the changes to the regulations in 2014, thousands of applications came in. They'll be built for the next 10 years, so you won't see a zero carbon house by a house builder for 26 or something.
No.
They won't build any.
It's not until we start building much more airtight, much more insulated dwellings that people will actually realise that the dwellings aren't performing as anticipated. At the moment, unfortunately, because people don't really know, if the dwelling's supposed to be very low energy and cost you X pounds a year to run, you'll notice if it doesn't. It's a bit like your car. If it's designed to do 50 miles per gallon and it doesn't, you notice it. But if you don't really know how it's supposed to perform in the first place, and you're quite happy paying what you're paying, it doesn't make a significant impact.
Yeah, I mean, industry's not interested in this at all. House builders are not interested in
Not
this.
the volume builders.
No.
I agree completely.
Well,
Well, that's a policy question for government and regulation, isn't
Yeah,
it?
an example
The-
of a recent procurement exercise we've undertaken, where we asked for these air tightness fixed, and they didn't comply with it and said, well, we're not really going to run the risk of putting the mechanical ventilating system in because it will cost more and it might therefore mean we wouldn't get the win the procurement. They didn't win anyway because they didn't comply with the bid, so I'm not quite sure what their point was. But the point is, sorry to interrupt, they took the view that it wasn't worthwhile doing.
Okay. But David,
Yeah.
David, a very a very valid point. But the impact of research is always felt later.
I hope
So one trusts that this research will lead to benefit
Pioneers.
in REF 2020, and we will be seen as pioneers. And David in particular. I have two further, one at the back and then one here. Okay. So.
Yeah, I think my question partly has been answered, but I think just as an addition to the issue of prediction, the predicted values are based on the existing as well as new homes, and by proportion one would think the existing homes have a much more impact on whatever is predicted. So in answer to the question as to whether we'll be able to fulfill, I mean, what we're doing is just scratching at the surface because the bulk of the stock is still existing and we don't have better methodologies to resolve
It is a
issues.
law.
The second question I was going to ask is, I mean, within your research, do you have any remit to think about better ways of undertaking your tests? You made references to the car manufacturing sector, where if you have got an existing car, even if it's 10 years old, you just plug into a machine and the testing method is not contributing to the negation of whatever you're trying to achieve. So within your remit of the research, is there any room for thinking about better ways of testing on existing buildings?
There is. Well, the protocols for testing existing new buildings are the same. There's no real difference between it. The issues are quite different. Getting the prediction right is incredibly problematic with existing properties because we've got much less idea about the performance. But the way you would undertake a cohesion test on an existing property is the same as you would on a new build dwelling, and the same with in situ heat flux measurements as well. One of my colleagues who's sitting in here, I don't know, maybe he's somewhere about here, Mr. Farmer, yeah, there he's there, keeping quiet. He's doing a PhD with us and he's in the process of looking at the cohesion test and looking at developing a much simpler way of undertaking the test to some degree, a simpler variant of what we originally do. So we are being pretty pioneering in terms of developing the protocol in terms of where it stands now, and are looking at more commercially orientated tests. So again, it's very difficult to get, I think, a commercial test. There are other organisations, so there are some very large manufacturers developing testing protocols as well, which they're looking at benchmarking against the cohesion tests. But that's something, yeah, certainly we are looking at, and we would be looking at helping them develop their testing methodologies.
A final question.
Just one question. One of the 4 factors that you mentioned about affecting building performance gap is about occupancy.
Yeah.
Is the gap bigger if you measured with the occupants in it, or is that's the result?
Well, we're specifically just looking at fabric as built.
Right.
So you would have to do the phase 2 projects, TSB projects. We're looking in terms of occupancy, but occupants can undo a lot of the good work that's done in terms of fabric if we don't, if they're not.
That's controversial. It wasn't for the users. These computers will be fine.
Yeah, I mean, if quite often they will use the building and certainly our experience with the passive house developments is the occupants have used the dwelling in the same way as they would have used any other conventional type of dwelling, and they require to be operated in a very different way. So that can have quite a negative impact on performance. The question is just to make it's more about robust design. We should feed back into the design process. So the design should be sufficiently robust. I suppose a bit like your car, but yeah, the range of performance, we know what the range is. If you put the foot down on the accelerator and floor it, you'll get this performance, and if you're a bit lighter footage, you'll get this performance. But unfortunately, we're house, and we just don't know. The designs aren't robust enough to do that.
Okay, well, thank you very much, David, and thank you all for coming this evening. And thank you, David, for sharing some of the work you've been doing, this more recent work, which is obviously of interest. I don't think I've fielded quite as many questions at a session such as this, and we've had a number over the last few years. But thank you very much for taking part, and just finally to thank David again in the usual way.